Simulating chemical engineering applications. The equations that describe fluid flow and chemical reaction, along with the transport of mass and energy, are used to describe and simulate applications in chemical engineering. While the scales may differ significantly, the physical phenomena remain the same. Transport phenomena in chemical engineering applications is divided into three areas: the transport of mass, momentum, and energy. Each area can in turn be subdivided into groups covering various transport mechanisms and requiring different equations to describe them. A system and its transport equations can also include and be influenced by chemical reactions. In chemical reaction engineering, the goal is to understand how chemical reactions influence a given process, and to use that knowledge to achieve goals in development and design. Structuring the development of a chemical process would require that you first model the chemical reactions in a perfectly mixed system, so as to investigate and determine the participating reactions and kinetics in a reaction mechanism. Once these have been determined, you would then consider the conditions your process will be subjected to in a reactor, where material and energy balances must be coupled and solved with fluid flow and reaction kinetics. A classic case for simulating transport and reaction processes is in the field of catalysis and reaction engineering. Simulation is often required to optimize the reactor or catalyst to ensure minimal material loss at lowest possible energy consumption. Models coupling mass, energy, and momentum transport, as well as chemical kinetics, are often required for accurate simulations of such. In addition to using resources efficiently, chemical engineers are also concerned with the regeneration and recycling of effluent streams from chemical processes. In water treatment facilities, an important part of the purification process involves separating solids from water, often in clarifiers. To model and optimize such a process requires multi-phase models for the fluid flow. Freeze drying is a common process for drying heat-sensitive products in the pharmaceutical, bioscience, and food industries. Water is removed through the sublimation of ice, leaving a porous material when the process is finished. The location of the ice boundary is therefore critical to describing, simulating, and designing the process and ensuring product quality. In the production of bulk chemicals, small improvements in unit design or process operating parameters leads to large savings in costs. Careful placement of heating pipes in this steam reformer, for example, is imperative for ensuring the endothermic reactions will occur at the optimal rate. Once again, the outcome of chemical reactions is governed by the distribution of chemical species, temperature, and fluid flow. Emulsions find wide application in the production of food, cosmetics, and household products. The properties and quality of an emulsion typically depend on the size and distribution of the droplets. To model such an application requires a multi-phase flow model capable of tracking the interface between immiscible fluids. The polymer industry makes use of petrochemicals to produce plastics. In this case, the mixing of the reacting species is the design parameter that needs close consideration. Modeling polymerization processes invariably involves describing and solving highly coupled transport and reaction systems. In semiconductor wafer manufacturing, thin layers of controlled thickness are produced through vapor deposition. The chemistry of such must sometimes be separated between that which happens at a surface as opposed to the bulk. Combining such detailed chemical reaction kinetics with transport models allows for realistic modeling of the deposition process. Irrespective of the industrial application, fluid flow and chemical reaction coupled to the transport of mass and energy must be considered in order to fully simulate and understand a chemical process. This is just a short overview of the different areas and types of applications where simulations are important for product and process development. A large number of more detailed examples are found on this disk from different industrial and chemical engineering applications. We encourage you to browse through them to see your application being simulated.